Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. Today we are going to talk on module Structure of Glasses, and this module is under paper Ceramics. So after the completion of this module, you all should be able to learn structure of oxide glasses, several parameters describing the structure of a glass. Moreover, we will be able to understand the silicate glasses, including glass formers, intermediates and modifiers. Now come structure of oxide glasses. So, we will first discuss the silica glass. As mentioned earlier, besides the oxide glasses, other materials like polymers and metals also form glasses. Here we confine ourselves to the oxide glasses. A precise description of the structure of glasses is still a topic of research. However, a basic idea have remained essentially unchanged since the work of Zescherison dating back to 1932, which we have already discussed in the previous module. Any description of the structure of oxide glass has to be consistent with the observations that the energy of the crystalline form is not much different from that of the glassy form. Also, the density of the glass and the corresponding crystalline form are nearly the same, and in the X-ray diffraction pattern of the glass, the peaks occur at the same location as they do for the crystals. So only they are much broader as compared to pure crystals. These observations imply that the structure of the glass should be close to that of the corresponding crystal, only it should not have long-range order. Moreover, this is the characteristic of the crystalline form. So students, before moving further, let's discuss some basic ideas. According to the first idea about the structure of silicate glasses, the glass structure consisted merely of very small crystals or microcrystals. Their very small size led to the observed broadening in the X-ray peaks. As is well known that the width of the X-ray peaks increases as the size of the crystals decreases for the crystal size or grain size less than 0.1 micrometers. A measure of this width is the width at half maximum, that is, the width of the peak in terms of angle theta at half the peak height. Knowing this width, the size of the crystallite can be calculated using well-known Scherer's formula. However, when the size of these crystals is estimated from the observed broadening of the peaks for the case of silica, it comes out to be 7 to 8 angstrom. The size of the cristobalite unit cell is 8 angstrom. So this would imply that the crystallite consists of a single unit cell of cristobalite. To quantify as a crystal, it must contain a few unit cells. The microcrystal theory has therefore been discarded. The currently accepted model of the oxide glass structures is the random network model. As we have discussed in previous module that the idea was first proposed by Zescherison, who was trying to explain the glass forming ability. He talked of the glass structure consisting of a vitreous network. Subsequently, this came to be known as the random network model. The random network model. It can be discussed with reference to the silica glass. In the crystalline form of silica, cristobalite is the stable crystalline form. The structure of cristobalite consists of SiO4 tetrahedra with the tetrahedra linked at the corners in a regular manner. The silicon atom sits at the center of each tetrahedra and the oxygen atoms are at the corners. So students, you can see a two-dimensional representation of this structure below. So this is two-dimensional representation of a structure of the crystallite silica, which is shown in figure A, whereas figure B is of silica glass. You can see that the solid circles are silicon and the open circles are oxygen. So it is clear that the silicon atom sits at the center, that is the solid circle, and it is at the center of each tetrahedron, and the oxygen atoms, which are open circles, are at the corners. A random network structure from the crystalline structure can be constructed if the SiO-Si bond angle spanning two tetrahedra is allowed to vary. This case is shown in figure B. A further contribution to randomness would be if the tetrahedra are allowed to rotate by random angles about the oxygen at which the two tetrahedra are linked. These factors would introduce randomness in the structure. The small range order observed in glass would also be present over the extent of tetrahedron, which is the basic building block of the structure. You can see two figures. So on the right hand side, figure A. In figure A, two SiO4 tetrahedra linked at the corners are shown. Here, the solid circles are silicon, whereas the open circles are oxygen. The bond angle for the bond SiO-Si is also shown in figure, which is represented as theta. In the glass structure, this angle varies over a much wider range as compared to that for the crystalline solid forms, that is cristobalite. So you can see from figure B, which shows the distribution of SiO-Si bond angle in the fused silica and in the crystalline cristobalate. The much wider variation of the SiO-Si bond angle results in random network structure. The structure of the silica glass can be rather well described by the random network model, in which the tetrahedra are linked at the corners with variation in the SiO-Si bond angle as well as random distribution of the angle of rotation of one tetrahedra with respect to another. So you can see in figure B that the distribution first increases, reaches its maximum value, and then decreases. However, in general, to describe the structure of a glass, several parameters would need to be specified as discussed by Shelby. These are briefly described as, so first is coordination of all the cations in the network, particularly the coordination of the cation in the basic building block of the structure. These coordination numbers can be estimated on the basis of the anion to cation radius ratio. At present, techniques such as magic angle spinning nuclear magnetic resonance, that is mass NMR, MAS NMR, can yield this number directly. Next is bond angle distribution and the distribution of the rotational angles between two building blocks. This is very much difficult to determine. Network connectivity. In a glass structure, there may be non-bonding oxygens, that is NBO, present due to the presence of some cations, as we will see while discussing the structure of silicate glasses in the next section. The network may be therefore broken. However, it is also possible that a change in the coordination from say 4, that is tetrahedral, to 3, that is triangular, may be able to satisfy the requirement of charge neutrality with no NBO present. A nil NBO may therefore be due to change in coordination. The dimensionality. The dimensionality of the building block needs to be specified. In case of silica, it is a tetrahedron with a dimensionality of 3. In B2O3, the unit is a triangle. The sheets are crumpled into a three-dimensional form to provide the 3 dimensions, that is the third dimension. In case of the long chain polymer, the chains are one-dimensional. Their folding in 3 dimensions provide the other 2 dimensions. So the next is range order. There may be intermediate range order present. Thus, the building blocks may arrange themselves in the form of chains or rings, giving order over a longer range than provided by the basic building block, and the intermediate range order will need to be specified. Next is the properties of the glass dependent on its morphology is also there. There is the phenomena of phase separation in glass, due to which a single glass can break into 2 glasses of different compositions. The morphology of these phases would need to be specified. Next is, there is always 3 volume present in a glass structure. This is present as void spaces between the tetrahedra. This free volume has an important influence on the properties of a glass. So this is in continuation with the silicate glasses. So you can see a table for some silicate network structures formed when the ratio of oxygen is to silicon is more than 2. So in this table, you can see on the left hand side, it shows the oxygen is to silicon ratio, and on the right hand side it resembles the structure. So one can observe that the first case, that is oxygen to silicon ratio, is 2. This means that one oxygen is shared by 2 silicon. Remember that the open circles or hollow circles resemble oxygen, whereas solid circles resemble silicon. So this type of structure is network structure. So you can see the next example, which has oxygen is to silicon ratio as 3. This means that one silicon is shared by 3 oxygen, and this forms chain or ring-like structure. Now let's move on to silicate glasses, that includes glass formers, intermediates and modifiers. We saw in the previous slide that the oxides such as B2O3, SiO2, GoO2, P2O5, AS2O3 and many more are able to form glasses. The cation in these compounds are called glass formers. So what happens if a non-glass forming oxide is added to a glass forming oxide? Then the silicate glasses contain the silica and alkali or alkaline earth oxides. When an alkaline oxide, for example Na2O, or alkaline earth oxide, let it be CaO, is added to silica, the oxygen to silicon ratio is increased. So according to rule number 1 of the Zicharison, which we have discussed earlier, the coordination of oxygen should be 2 or less. So to maintain the glass network structure, some of the oxygen therefore remain unbounded in these glasses. That is, they are singly bonded oxygens which do not take part in the network formation. Modifiers. The alkali or alkaline earth ions, because of which the network structure is modified, are called modifiers. To maintain the charge neutrality, they position themselves near the single bonded oxygens which are shown in this figure. So this figure shows the location of the network modifiers in the silicate glasses. So you can see that the hollow circles or the open circles are oxygen, whereas the solid circles are silicon. You can see that the oxygen which is connecting one structure to another is called the bridging oxygen, whereas the oxygen which is not connected to another structure is called non-bridging oxygen. However, there are silicons which are present in between, which forms the network formers. So students, you can also see that there are some which are present in between are known as modifiers just to maintain the charge neutrality. In the structure of the silicate glasses, we have seen the network formers, that is Si, network modifiers, that are alkali or alkaline earth cations. We have seen the bridging oxygen and non-bridging oxygen, which are known as NBO. Each alkali ion creates one new NBO, that is non-bridging oxygen, and each alkali oxide molecule R2O creates 2 NBO, that is non-bridging oxygen, as depicted in this figure. Adding alkalis increases the density of the glass because it fills the holes in the network, which can be seen in this figure shown below. Therefore, the alkalis are fluxes. They determine the viscosity of glass by several orders of magnitude and decrease the value of Td. It increases the refractive index, density, the coefficient of thermal expansion, and increase the electrical conductivity. The number of the NBOs created by adding the alkali oxide can be correlated with the changes in the properties of the glass. The number of the bridging and the non-bridging oxygens can be related to the average number R of the oxygen ions per network forming ions, or the oxygen-silicon ratio in case of alkali silicates as follows. Now let us consider some examples. Consider a glass with X mole fraction of an alkali oxides A2O and 1 minus X mole fraction of SiO2. Then the total number of oxygens are equal to X plus twice of 1 minus X, which comes out to be 2 minus X. The oxygen to silicon ratio is given as capital R, which is equal to 2 minus X divided by 1 minus X. Consider a glass with only one type of network forming cation surrounded by Z oxygens. Here Z is equal to 3 or 4 and it is 4 in case of silicates. Let there be X non-bridging oxygens and Y bridging oxygens per silicon. So, the equation becomes X plus Y is equal to Z and X plus 0.5 times Y is equal to R. If oxygen polyhedra are SiO4 polyhedra, then Z is equal to 4, so that X comes out to be 2R minus 4 and Y is equal to 8 minus 2R. As an example, consider a glass with the composition Na2O times 2SiO2. In this case, R is equal to 5 by 2, as we know that R is oxygen to silicon ratio. So you can see that in the formula of Na2O times 2SiO2, number of oxygens are 5, whereas number of silicon are 2. So the ratio becomes 5:2, which comes out to be 2.5. Now substituting the value of R and calculating the value of X and Y, we get X is equal to 1 and Y is equal to 3. The values of X, Y, R are already given in the table which we have discussed earlier for few glass compositions. Alumina, that is Al2O3, does not form a glass. One can work out and show that it does not satisfy the Zacharyson rules for glass formers. However, aluminosilicate crystal satisfy the Zacharyson's rule, as for it the aluminium coordination number is 4, while the oxygen coordination number is 2. Thus, aluminosilicates are able to form glasses. The oxides such as Al2O3, which do not form glass by themselves but are able to form a glass when added to others, are called intermediates or conditional glass formers. Some of the examples of the network formers, intermediates, and modifiers in glasses have already been discussed earlier in the previous module. Now let's discuss some glass compositions. Properties of oxide glasses can be tailored to suit a given requirement by controlling its composition. The basic constituents of a silicate glass are SiO2, Na2O, and CaO. As an example, in fiberglass, Na+ can react with moisture and degrade the glass. This can be significant because of the large surface to volume ratio of the fibers. To overcome this problem, Al2O3 and B2O3 are added. These are trifunctional but go into the network and reduce the network modifier's need. So you can see the composition of some of the common glasses in this table. So some of the glass types are fused silica, borosilicate, containers, float lamps, and so on. So you can see that most of the SiO2 are utilized in forming the fused silica. Aluminosilicates are an important class of glasses. They are used as alkaline earth aluminosilicate fiber glasses, alkaline aluminosilicates for ion exchange, and lithium aluminosilicates for glass ceramics. Aluminium replaces some of the silicon ions in the network of glass. As Al2O3 contributes only 1.5 oxygen per network ion, some of the non-bridging oxygens are used up and converted into bridging. The effects of alumina is to increase the viscosity of glass and to increase the elastic modulus and decrease the coefficient of thermal expansion. You can see the figure of Al2O3 where Al2O3 addition increases the conductivity of an alkali modified glass. The non-bridging oxygens are replaced by AlOSi bonds. So on the left hand side, you can see that the NBO, that is non-bridging oxygens, are getting replaced. So students, let's now summarize what we have learned in this module. So we have observed and understand the observations that the energy and the density of the crystalline and the glass form an oxide are nearly equal to the conclusions that the structure of the glass must be similar to the crystalline form. Only it would not have the long-range order of the crystal. Moreover, the Sharrison proposed the random network model of the glasses, and in the random network structure of glass, the bond angles are not fixed but are allowed to vary by a small amount. Also, a random rotation about the SiO-Si linkage is permitted. In the silicate glasses, we have learned that beside the glass formers, there are other elements which are also present, and when an oxide, which is not a network former, is added to a network forming oxide, some of the oxygen remain unbounded to maintain the coordination of oxygen at 2 or less according to the Sharrison rule. The network structure is therefore modified, and the alkali or alkaline earth ions which modify the structures are called modifiers. So to maintain the charge neutrality, they position themselves near the singly bonded oxygens. And in the structure of silicate glasses, we have network formers, that is silicon, network modifiers which are alkali or alkaline earth cation. We have also seen that bridging oxygen and non-bridging oxygens are also present. So each alkali ion creates a new non-bridging oxygen, and each alkali oxide molecule, that is R2O, creates two non-bridging oxygen. Some oxides do not form a glass by themselves, but when they are added to a glass forming oxide, they enter a glass network, and these are called intermediates. We have learned that one of the example of intermediates are aluminium, which we call as aluminosilicates, which are the important class of glasses, and they are used as alkaline earth aluminosilicates fiber. So in this case, aluminium replaces some of the silicon ions in the network of glass, as Al2O3 contributes only 1.5 oxygen per network ion, and some of the non-bridging oxygens are used up and converted into bridging oxygen, and the effect of alumina is to increase the viscosity of glass, thereby increasing the elastic modulus and decrease the coefficient of thermal expansion. Thank you.